from the Zürich University, and the title is Distal Systems in Topological Dynamics and Ergodic Theory.
Okay. Yeah, thank you for the kind invitation. I'm happy to be in the seminar and to be able to give a talk about this project, especially since it's a project that Henrik and I have been working on for a long while. Yeah, and so I imagine that many of you have maybe heard about distal systems or are familiar with the terminology around distal systems, but I'm not sure whether everyone is familiar with the terminology. And in either case, I will need to introduce all of it again briefly. But I think I have like a somewhat different perspective than usual on distal systems. So I like to motivate it like this. We start with a linear dynamical system. So basically the most simple dynamical system one can imagine, just a matrix on some C to the n. And via the Jordan normal form, we can assume that this matrix is, after a basis change, just a Jordan block. And in that case, the action is given very simply. I mean, we have just here in the last component multiplication by lambda. So here we have an eigenvector, and then we have something which looks like an eigenvector identity, but we have this error term which depends on the component which comes before, and the same in each component. So we always get this kind of perturbation term which comes from the component before. And one can also rephrase this by saying, in fancy words, that this vector space admits an A-invariant decomposition, which we get by starting with the null space, and then we take this V1, which consists just of the last component. So basically, it's just the eigenvectors. And then we take V2, which consists of the last two components, and so on. And all of these subspaces are invariant, and I have canonical projections from one subspace to the next subspace. And as I said, this V1 encodes the eigenvectors, and the higher Vj's, they encode like generalized eigenvectors of order 2 and so on. And the Jordan normal form is, of course, super important for all kinds of applications. But I mean, it is limited to linear dynamical systems on finite dimensional spaces. So it makes sense to ask whether one can use this idea of having such normal form also for nonlinear dynamical systems. And this is this is also a way in which one can view distal systems and structure theory of distal systems as viewing it as normal forms for dynamical systems. And so we start with a topological dynamical system, K phi. This for us just means that we have a complex space and the homomorphism on the space. And then the question is, okay, if we want to have like such a decomposition, we need some notion of systems which consist purely of eigenvectors, or which can be described in terms of eigenvectors. And these are precisely the isometric systems. So systems where we can find a compatible metric on our space, which is invariant under the dynamics. And we will also need a slightly more general notion later on, where we say that the system is pseudo-isometric if the same is true, but for an entire family of pseudometrics that generate the topology of the space. This is necessary if you have a space which is not metrizable, which we will have occurring later on. Okay. And the standard example is, of course, the irrational rotation, which we will see quite a lot in this talk. So we have an alpha in T in the one-dimensional torus, the circle, irrational, which is fixed throughout the talk, and then we rotate. And the system is isometric, and it's also minimal, which means that every orbit is dense. Moreover, as I indicated, we have lots of eigenvectors. So if we consider the Koopman operator, the induced action on the space of continuous functions, then this operator has a ton of eigen functions, namely the characters, and these actually span the entire space of continuous functions. Let's remove this. Okay, and this is not a coincidence because there's the following theorem. This theorem says whenever you have a topological dynamical system, then it is pseudo-isometric, depending on whether it's like second countable or not, if and only if the entire space, C of k, of continuous functions, is generated by Eigen Functions of the scope 1 operator. Okay, so isometric systems in this sense are can be described, or are systems which can be described in terms of eigenvectors and eigenvalues, and can therefore serve in analogy to the orthonormal form as elementary building blocks for more complicated dynamical systems. And if you want to build more complicated dynamical systems, then we need to have some notion of generalized eigenvectors, or some kind of, yeah, a way of making this more extending dynamical systems. This leads us to the notion of extensions. So an extension is just a quotient map of dynamical systems. So we have continuous surjective map such that the diagram which you want to which you would like to commute, it just commutes. And such an extension is isometric if, and now we would need a tiny bit of notation. So by k index small l, we denote the fiber of k over L with respect to this quotient map. And here we have the fiber product of k with itself over L. So we take all points in the product which project to the same thing on L. And then we want that there's a continuous map on this fiber product to the positive real numbers such that, well, if I restrict it to a specific fiber, then it is a metric compatible with the topology on this fiber. And it is supposed to satisfy, again, the obvious invariance property. And all of this just means that one has a quotient map, and on the fibers of this quotient map, one has a continuous family of metrics which satisfies an invariance property. And the standard example, which also is going to stay with us for the rest of the talk, is the skew rotation. So here at the bottom, we have the irrational rotation, which we're already familiar with. And at the top, we have the map which maps x, y to alpha x in the first component and xy in the second component. And if we then project to the first component, we see that the diagram commutes and we get a quotient map and hence an extension of dynamical systems. And this extension is isometric because you can just take as this distance function or fiber-wise distance function, the distance in the second component. And then you can easily verify that this is indeed invariant. Okay. Now, a topological dynamical system, K phi, is called distal if for any compatible metric D, or a family of pseudometrics, if you do the more general setting, if you take 2 points which are different, then, it appears there's something missing here. So here, this should be greater than 0. Sorry for that. If you have 2 points which are different, so the distance is greater than 0 or different from 0, then also the infimum over the entire orbit of the distance is greater than 0. So it's or different from 0. This just means if you start with 2 different points, then neither in the past nor in the future can they, along some subsequence, converge arbitrarily close together. So they stay separated or at a certain distance of each other. And these systems are interesting because, first of all, the skew rotation, which we just saw, is easily verified to be a minimal and a distal system. And this is interesting because there's a structure theorem which more generally says that the systems which are minimal and distal are of this form as the skew rotation. So if you have a minimal distal system, then Furstenberg tells you that this minimal distal system decomposes as a tower of isometric extensions in the following way.
Excuse me, can you return to the example in the previous slide where you defined the, because yes, you are supposed also to give the metric when x1 and x2 are different, right?
No, so this is because I'm taking the fiber product over the projection onto the first component. So in this case, this map Q, the quotient map, is the projection onto the first component. And the fiber product consists of all pairs for which this projection onto the factor is the same.
And the metric, okay.
Yeah, so it's not globally defined. It's only defined on this fiber product. So it's kind of hidden here in the index. So it's really just a fiber-wise metric. You could also say you have a family of metrics. For each fiber, you have one metric and then a continuity condition. It's equivalent.
I see. Okay.
Is it okay, so?
Yeah, now I see on KL. Yes.
Okay.
Sorry, I'm still a bit confused about that. Could you please return?
Yes, sure.
So what is the second condition for any x, y in k times k? So I'm confused. If you have points from the same fiber, they are projected to the same point, right? Or I'm missing something.
So here we take 2 points from the same fiber. And then we apply the dynamics to these points.
Oh, I see.
We don't apply the projection Q, we apply the dynamics. This is important. And this just says that if I take 2 points in the same fiber, then they get mapped to another fiber. But in this target fiber, the distance is still the same. Okay. If there are no further questions for this slide, then I will go back to the Furstenberg structure theorem, which looks like this. So if you have a distal minimal system, then here at the top, this is the distal minimal system, and it can be built up by starting at the bottom with some isometric system, then taking an isometric extension of this isometric system. And this is exactly what we saw for the skew rotation. So we had the usual rotation at the bottom, and then we made an isometric extension, and we got this dynamical system on the two torus. And Furstenberg tells us, okay, if we keep iterating this procedure, then in that way we get all distal minimal systems. Okay. Now, okay. So this is already a very powerful structure theorem, but somehow it inspired another structure theorem, which is even more powerful and has even more applications. And this is a structure theorem in ergodic theory. And that's the Furstenberg-Zimmer structure theorem. And just to fix my notation so that everyone knows what we're talking about, in this talk, a measure preserving system consists of a probability space, which I assume to be separable just for the sake of simplicity, and a measurable, essentially invertible map, phi from x to x, which is, well, measure preserving in the usual sense. I could also do more general group actions, but there is one very, very crucial point where everything fails for general group actions, or at least we don't know how to do it for anything other than Z actions. And I will say where this is, but apart from that, everything works for general group actions. Okay, and now we already saw that systems for which we have a lot of eigenvectors, and one can do the same thing in ergodic theory. So a measure preserving system has, and here one says discrete spectrum, if the Koopman operator T phi from L2 of x to L2 of x satisfies that the entire L2 space is generated by Eigen Functions. And one has to use here the functional analytic description because one has no metric which one could use to try to do something on the point of on the level of points. So one has to work on the functional analytic level here. Okay, and the usual example is, of course, again, the rotation. So this has discrete spectrum since, well, what are the eigenfunctions? The eigenfunctions are, again, just the characters as in the topological setting. And here they are even an orthonormal eigenvector basis. So in particular, they generate all of L2 of X. Okay, so now we do the exact same thing that we did in the topological setting, also in the measure-theoretic setting. An extension here is again kind of a quotient map. So we have a measure-preserving map from X to Y, where I usually just omit the sigma algebra and the measure. So this is implicit. Unless it's necessary, then I will specify them. And yeah, this extension, this map pi, should satisfy that the usual diagram commutes. And then one can prove the theorem by Furstenberg and Zimmer, for which one would need two notions with that, which I have not yet defined, but I will say something about that in a minute. So we start with just some measure-preserving system at x phi, and then this system decomposes as a tower of extensions in the following way. And note that in contrast to the topological setting, I did not assume that we have, for example, a distal system here. Okay, the resulting tower looks like this. As in the topological setting, we start with the part which captures somehow the eigenvectors, the discrete spectrum part at the bottom. And then we make extensions. In the topological setting, we took isometric extensions. Here we take extensions with what is called discrete spectrum, which I have not yet defined, but will do later. And then we keep going like this, and we take extensions with discrete spectrum and so on and so forth. And in the end, we not necessarily reach our system with which we started, but we reach a smaller system, which still has the nice property that this last step, the gap that we cannot bridge with discrete spectrum extensions, is an extension with a special property, which is called weakly mixing. And this is not going to play a role in this talk. So this is also why I drew it in gray. So I'm not going to define this particular notion. The applications of this structure theorem are, they are. So I think, the most well-known is, of course, Furstenberg's proof of Stemmeridis' theorem on arithmetic progressions, which used this idea of taking your system and decomposing it into a structured and a chaotic part. So the discrete spectrum would be the structured part, and the sweet mixing would be the chaotic part, to prove general recurrence phenomena for measure-preserving systems in high generality. Now, this is not what this talk is about. So one could fill an entire talk with just proving all of these theorems. This talk is about observing that they look very much alike. And this is, of course, no coincidence, because as I said, the Furstenberg structure theorem on minimal distal systems inspired the Furstenberg-Zimmer structure theorem, which was later. But it looks like one is doing somehow 2 times the same thing, but it's just an analogy. And sometimes it makes sense to ask, is it really just an analogy? Because it's very suspicious that one does very similar things 2 times. Maybe there is more going on here. And this is the question that I would pursue in this talk. And to that end, we introduce the following definition. We also say what it means for a measure-preserving system to be distal. And we just call it distal if we don't need this gap here with the weakly mixing extension at the end. So X is already equal to this X omega, which means that we can start with a discrete spectrum system and build our desired system up by using discrete spectrum extensions. Okay. Now, here's an example for what this looks like. That's, of course, the example that we've already seen. We take the skew rotation with, well, the canonical measure. We take the Haar measure. And then one can ask, what does this tower look like? And as for the topological setting, the tower is exactly the same. So the part here with the discrete spectrum, this will be the rotational factor. And then we will have here our original system, and this here will turn out to be an extension with discrete spectrum, but we will get to that. So now, the question whether these two types of systems, distal systems in ergodic theory and distal systems in topological dynamics, whether they are related, this is, of course, not a new question. So one direction is very easy. If you start with a minimal distal topological dynamical system, and you have some ergodic measure, which is invariant on this system, then you get a measure preserving system by just endowing this topological system with this measure. And then one can show that this system is also distal as a measure preserving system. This direction is not so hard. The interesting question is, so we can get from a minimal distal system to some ergodic distal system by just picking some ergodic measure. What about the other direction? So if we start with an ergodic distal system, can we get some minimal distal system out of it? Maybe can we represent ergodic distal systems as minimal distal systems? And what do I mean by this, by representing it as? This means finding a topological model for a measure preserving system. And this I define as follows. So a topological model is a topological dynamical system K psi with, okay, this here should read psi, with an invariant measure on this on the system. And it should be isomorphic to the original system in a certain sense. And one might be tempted to use point isomorphy here. So just find some map from X to K, which is almost invertible or essentially invertible. But it turns out to be very important to have more flexibility here. And because if you have no longer study systems which are separable, so if X or K is not a separable measure space, which can happen, then you run into trouble with finding these point isomorphisms. And then a more flexible notion of isomorphism on the functional analytic level is more natural and more versatile. And it can do exactly the same things that you need, because usually you always end up working on the functional analytic level. So it reads as follows. You have an invertible isometric Markov operator from L2 of X to L2 of K mu, such that, well, again, some diagram commutes. So the dynamics of the Koopman operator on L2 of X and the dynamics of the Koopman operator on L2 of K are related via this isomorphism phi. And if K is a compact metric space, and if X is a separable measure space, which I always assume, then this is the same as saying these systems are point isomorphic. But it will happen that K is not a compact metrizable space, and then this is not the same. But for simplicity, you can just think of point isomorphy. So, and then we have the following theorem of Lindenstrauss, which actually already answers the question. So, if you have an ergodic distal system, then it has a topological model that is minimal and distal. Okay, nice. Question settled. Well, not quite. So if you look into the proof of Lindenstrauss, then what he does is it involves a lot of choices, and especially non-canonical choices. So he has to work very hard to construct this topological model. And in the end, the model he obtains is not canonical. And Henrik and I, we went back to this, and we thought a lot about this connection between topological dynamics and ergodic theory. And somehow we ended up realizing that one can do things in a more systematic way, and then actually obtain that this relationship is completely canonical and in fact functorial. So one don't has to make any arbitrary choices. One just gets a very canonical map from ergodic distal systems to minimal distal systems with some invariant ergodic measure. And perhaps more interestingly, one also learns a lot along the way. So this is actually more of the focus, all the things that one learns along the way about dynamical systems. And to prove this theorem, or to think about how one can prove this theorem, it makes sense to first ask an easier question. And this is the following theorem, the special case. We start with an ergodic system with discrete spectrum. Certainly is an ergodic system with discrete spectrum is distal as a measure preserving system. And then one can show that such a system has a completely canonical topological model, no choices required, on a minimal distal system. In fact, a minimal isometric system. Okay. Now, if one wants to prove this, how does one go about it? How does one construct topological models? This is the content of the following slide, which is a brief reminder or a brief introduction to the machinery for constructing topological models. Because you just have this measure preserving system, and now you're supposed to suddenly find some topological structures somewhere.
May I ask a question?
Yes, sure.
Regarding the previous slide.
Mm-hmm.
So the special case, I mean, when I think in the separable case, this seems completely trivial, but you are stating it, I'm talking about the second theorem.
Yes, exactly, yeah.
Why, so is this like non-trivial when you start working in non-separable?
Oh, it's not more difficult when you work in the non-separable case. I will give a proof, and it's going to be very simple.
But isn't it the case that discrete spectrum system, ergodic discrete spectrum system, is a minimal rotation? So what is I don't understand why this is new, let's say.
It's not new. No, it's not at all new. I'm not claiming it's new. It's really.
So, would you agree that at least this case, the canonical representation is known?
Yes, it definitely is known. I'm not going to. I was not planning to talk about it. I just wanted to show that later it's a minimal isometric system, which of course are rotations or rotations in homogeneous spaces, and it's not difficult, and it's well known, of course. But I want to prove it, because later we will prove something more complicated, and then it's good to have the intuition.
I see. Okay.
Yes. Okay. So now topological models. How do you go about this, finding a topological model? If you have just a measure preserving system, where do you get a compact space from? Okay. Well, let's say we have such a measure preserving system. And suppose we have some subalgebra of L infinity of x, C star subalgebra, which is dense in L2. So for example, you could just think of A equals L infinity of x. This would be totally admissible. Then Gelfand's representation theorem on commutative C star algebras tells you that there is a C star isomorphism from this algebra R to some C of K. So to the algebra of continuous functions on some compact space K. And via this isomorphism, you can also take this measure mu, and you can pull it over to get a linear form on C of K. And this, again, via the Riesz-Markov-Kakutani theorem, can be represented by a measure mu K on this compact space. So what we've done now is that we've started with our measure space, and we constructed a compact space with a measure which comes from the original measure. Now we need to also pull over the dynamics. So we consider the Kopman operator on an infinity of x. And if the algebra A, if we assume it is invariant, then this induced isomorphism phi can be used to also obtain an induced operator T on the space C of K. But for that, it's important that the algebra A is invariant. And then Gelfand tells us, well, if you have C star homomorphism on some C of K, then it is already a Kopman operator for some unique continuous function. Okay, and now what remains? What now remains is to see that phi actually yields an isomorphism on the level of L2 spaces. Oh, that was too much. So since this algebra A is dense in L2, and the measure on K was just essentially the measure on X pulled over via phi, one can easily check that phi extends to an isomorphism between L2 of X and L2 of K, mu K. And then, yeah, essentially all the things that one needs for a topological model are verified. So the trick for finding topological models is to find a good subalgebra A, C star subalgebra of L infinity of X, which is invariant and dense in L2 of X. And this is very important. We will run into a problem with this later on in the talk. It's essential that the algebra is dense for this last step so that you can extend this isomorphism to all of L2 of X. For example, you could think of the simple algebra A, which just consists of the constant functions. I mean, this is not going to give you a meaningful topological model. The compact space that you get will just be a point. So it's really, really important that A is dense in L2 of X. Okay. Is there a question about the construction of topological models at this point? Okay, there does not seem to be one. So then we will move on. And yeah, we revisit this theorem, which, yeah, as Jonathan said, is well known. Every ergodic system with discrete spectrum has a canonical topological model on a minimal pseudo-isometric system. And one can actually show that they are rotations, but I'm not going to need this here. Okay, and the proof is actually, yeah, relatively simple. We want to find a topological model, so we need to write down some C star subalgebra. And what we do is that we take all eigenfunctions, and then we take the linear span of these eigenfunctions and the closure in L infinity of X. Because the system is ergodic, the product of eigenfunctions is again an eigenfunction. And so this is actually already a C star subalgebra. And so it yields us a topological model because by assumption, this here is also dense. Okay, so we have this topological model now, and it satisfies two things. By ergodicity, we know that there are, well, almost no invariant functions. So the fixed space of the Kopman operator T psi on this compact space K is just the continuous constant functions. And we also know that C of K is the linear, closed linear span of the eigenfunctions. And, sorry, this here should be C of K. Here I forgot to apply the isomorphism. And this just comes from the definition of A, because A in the end is isomorphic to C of K, and the dynamics on A becomes the dynamics on C of K. Now, earlier we saw this characterization theorem, which says a system is isometric if and only if, well, C of K is generated by eigenfunctions. So we can already conclude that this system here is pseudo-isometric. And now we only need to check this minimality part. And for that, we recall a fact from topological dynamics, namely, if you have such an isometric system, then it is minimal if and only if it has no non-trivial invariant functions. Okay, but we already know it has no non-trivial invariant functions. So from this, we can conclude that the system is minimal. And thus we have found a minimal isometric model, which is completely canonical. Because what did we do to find this topological model? We just wrote down this algebra A, which did not involve any choices. We just took all the eigenvalues and the eigenfunctions, and we stuffed them together and generated this C-star subalgebra, and we got a canonical model out of this. And that's the entire proof. Now, we are in the following situation. So we have these two different types of towers. We have the towers for distal ergodic systems on the left-hand side, which the Furstenberg-Zimmer structure theorem, which we see in the Furstenberg-Zimmer structure theorem. So at the bottom, we have this discrete spectrum system, and then extensions with discrete spectrum, and more extensions with discrete spectrum, and so on. On the right-hand side, in topological dynamics, we have isometric systems at the bottom, and then these isometric extensions, which go on, down, and on. What we have now seen is that there is a very canonical way of getting from a system with discrete spectrum to an isometric system, completely canonically. We can find a topological model. I mean, this makes you wonder, if you want to prove something here at the top for an ergodic distal system and a minimal distal system in topological dynamics, maybe you can do this by just doing the same thing you did down here, one step higher, and then one step higher, one step higher, one step higher, until you reach the top of this tower. Well, this would mean that we have to find even more topological models. So not just for x1, phi1, but also for x2, phi2. And now things are getting interesting because we need to find a topological model which maps for this discrete spectrum extension, which is an isometric extension. Now, how do we do this? Well, how did we do it before in the very simple case that we just saw? We started with some system x phi, and we wanted to find a topological model, k mu psi, with some special property p. In the example that we saw before, this property p was that the system should be isometric. The topological model should be isometric. And to do this, what did we do? First, we needed a functional analytic property q, which is equivalent to the property p. In our case, property p was the system is isometric, the topological model is isometric, and the functional analytic description is we have many, many eigenfunctions. And then we use this characterization to find a subalgebra A, which satisfies this property q, so that if we use it to construct a topological model, we will get the property p that we actually want. And so what we see is that it's very important when we want to construct topological models to translate the desired properties into functional analytic language. And this is exactly what we did here. So we had here the eigenfunctions, and then at the end we used that we get also this characterization in terms of functional analysis on the topological side, and then we use the equivalence to the property on the point level. Okay. Is there a question so far? It seems that not. So in that case, it's clear what we have to do. So we want to show, or at least better understand, why ergodic distal systems can be represented as distal minimal systems in topological dynamics. If you want to do this using the approach that I just outlined, we need to find a way to characterize isometric extensions in topological dynamics via functional analysis. And then constructing topological models will be hopefully as easy as we just did it on the previous slide. So let's try to do this. For the remainder of the talk, we will try to find a functional analytic characterization of isometric extensions. Then we will show that every discrete spectrum extension has a canonical topological model with this property. And discrete spectrum is still not defined, and I will only define it when I really need it, because later we will see why we will have a different view on discrete spectrum coming from a topological view. And then the final part that we need to do is work up the tower step for step to find models for increasingly complex distal systems. Now, the first question is always a feasibility question. Why should it even be possible to do this translation in one? So why should it be possible to translate properties into functional analytic language? Might be that by doing this transition to the Koopman operator, some information is lost, and so you cannot get a complete characterization. Well, actually, Gelfand tells you a bit more than I told you earlier. So the Gelfand representation theorem actually shows that there is an anti-equivalence of categories between, on the one hand, compact Hausdorff spaces, and on the other hand, unital commutative C-star algebras. And this anti-equivalence just takes a complex space and maps to the space of its continuous functions and maps morphisms, or surjective maps between, or just continuous maps between compact Hausdorff spaces to the corresponding Koopman operator. And the fact that this is an anti-equivalence of categories means that in principle, you should be able to translate any property in one category to a property in the other category. And this is precisely the content of the philosophy, which is called Koopmanism. So the philosophy is to use this equivalence of categories to translate or switch between the two categories at your convenience. Sometimes this works better, and sometimes this works not at all. And it's somehow one has to check in which cases it makes sense to do it and in which cases it does not. And as we will see, in this case, it makes a lot of sense. Okay. Now we start with this theorem that we've already seen. This is somewhat a starting point. For isometric systems, we have a very simple characterization in terms of eigenvalues of the Koopman operator. Now, it would be interesting to have this for extensions. We want to characterize isometric extensions in terms of functional analysis. How do we do this? Well, one of the things that it makes sense to do is to just have a look, first of all, at how one proves this characterization. And this characterization is proven by using this equivalent to the following characterization. So one can also ask that the subspaces F in C of K, which are finite dimensional and invariant, are dense in C of K. This is the same because in the end, one realizes that on these finite dimensional subspaces, the operator is, it's just a matrix and it ends up being diagonalizable there. So one gets the Eigen Functions back. Now, let's try maybe to understand how one would prove this theorem. And we only do one direction, which is a bit more the direction which is conceptually interesting, namely the direction where we start with an isometric system, and we try to see how we can get one of these two properties here. So yeah, well, let D be such an invariant metric on K. Then we can start with our system, and we can look at the acting group here. No, the phase. And this is the transition group. Transition group is the right name. I think Ellis calls it that. So the transition group, we just take the powers of our dynamics, and then we compactify it. This is the construction of the Ellis semigroup, which enters here vitally. So what you do is you take all the powers of your dynamics, and this is a family of functions from K to K. And then you can try to take the closure of this family of functions and from K to K in different topologies. And traditionally, the Ellis semigroup is defined as taking the closure in the topology of pointwise convergence. And then it ends, you end up with something which is again a compact topological space and also a semigroup. And this is the Ellis semigroup. In this case, if you start with an isometric system, you get a bit more than just a semigroup. Namely, you observe the following. So you take the set of all isometries of this compact metric space here. Then, well, this is an easy exercise to show that even if you take the topology of pointwise convergence on K to the K, this is a compact group in there, because for isometries, pointwise convergence and uniform convergence are just the same. Now, if your system is isometric, then all these powers here are isometries. And so you stay within this thing here, which is actually a compact topological group. And so the closure of the powers of your dynamics is contained in this compact group, and it's closed, so it is itself a compact group. Thus, we started with our isometric system, and we performed some kind of topological closure, and now we have this additional algebraic structure, or algebraic and analytic structure of a compact topological group, the enveloping group. How does this help us? Well, compact topological group, finite dimensional invariant subspaces, this smells like Peter Weil. And indeed, there's a version of Peter Weil for actions on Banach spaces, which goes as follows. Say you have a continuous representation of a compact group on some Banach space X, then you already know that this Banach space X is the linear closed hull of all the finite dimensional pi invariant subspaces for this representation pi. And this is super helpful because now what you do is just that you say, okay, I take this compact group here, I let it act on the space of continuous functions, and then I apply this Peter Weil theorem to conclude there are many invariant finite dimensional subspaces. First, these invariant subspaces are actually invariant for the entire compact group given by the Ellis semigroup, but we actually only need it for one element of the Ellis semigroup, which is equivalent, namely the Koopman operator T phi. Okay. And what we see now is that the proof actually is relatively short if you draw it in this, just in this diagram. Namely, you start with the system, you take the powers, compactify, apply Peter Weil, and then you're done. So maybe we have a chance of somehow adapting this proof. Let's see. Can we come up with a more general version for isometric extensions to have, to achieve our goal, functional analytic description of isometric extensions? To think about that, we first observe the following. So for a compact space K, we know that it is in one-to-one correspondence with this C star algebra C of K. So the right way, in some sense, to encode or view a compact space from the functional analytic point of view is to look at it as a commutative C-star algebra, or the commutative C-star algebra of functions on it. Now, what is the right way to think about extensions? So we have an extension of, or just a quotient map of complex spaces. And then how do we think about it? One way to think about it is to think of C of K as a C of L module. And this is somehow an important conceptual point here. Namely, we observe that functions, which are defined down here, on L, act on functions, which are defined up here, on K, in the following way. We take such a function on L and a function on K, and we multiply this function on K, or function G here, by, well, not exactly the function f, because the function f lives down here, but via Q, by composition with Q, we can make this function which lives down here to a function which lives up here on K, and is just constant on the fibers. And then we can multiply. And often people in ergodic theory actually don't make this distinction here and do not write this TQ here. So if you're more familiar to the situation where you do not have this TQ here, then that's also okay. You can just omit it later and implicitly have this module structure in mind. Okay, now, of course, a lot of things have already been done, and people already started thinking about how one could come up with functional analytic descriptions of isometric extensions in topological dynamics. So if you go into the infamous book by Ellis, and you look in the very, very last chapter, I think it's like almost the last theorem, then you will find the following, which is a result by Anthony Knapp. And he shows the following. So if you have an extension of minimal distal systems, then if the extension is isometric, one has a functional analytic property, which we are quickly going to analyze. So we have again a linear closed hull. So this is the same as before. And now we, of course, need something which is a bit more complicated than before. What we have are, instead of finitely generated subspaces, which are invariant, now we have finitely generated submodules, finitely generated C of L submodules, which are invariant. And one also needs this closeness property here when one goes to the relative setting of extensions. And this somehow falls into a more general framework of what one might call relative functional analysis. So you have all the usual concepts from functional analysis, like subspaces and operators and spectral theorem and morphisms and all of that. And then you go to the setting of modules, and then you get relative versions of all these things. And finite dimensional subspaces become finitely generated submodules, and so on. Okay. And if you are already familiar with the definition of discrete spectrum in ergodic theory, then this here looks very familiar. Now, this is already good, but there's a problem because we can't get back here. So we would actually like to go back here and also know that if this stuff here holds, then the extension is isometric. So we have the theorem by Knapp, but actually we would wish for it to be a bit different. We would like to have an equivalence. Okay, let's try to see whether we can get this working. The idea is as follows. For isometric systems, we now understand how one can prove such characterizations. You start with your isometric system, you form this group this transition group of the powers of your dynamics. You compactify it to obtain a compact group, an enveloping group, and then to this algebraic compact structure, you apply the Peter-Weyl theorem. Well, let's try to just do the same. So we start with an extension. Let's say the extension is isometric. And then, yeah, then the trouble begins, because then what do we do? I mean, we can't just take the same thing that we did up here and copy it, because then we just do the same as here, and we have no chance of actually arriving at this more complicated, more general statement. So we will need to put something different here. And maybe if we choose the right thing here, we can compactify it in some sense to get some compact object to which we then maybe, with a question mark, can apply some version of Peter-Weyl to then conclude that there are many finitely generated invariant submodules. Okay, well, there's a big question mark here. If we can't take just the powers of our dynamics, which makes sense because it would not take into account that we are studying an extension, it would just take into account the system at the top. If we cannot do that, what are we supposed to do? And now there is a conceptual shift that is happening. So we need to go beyond groups. And the problem is many objects that occur in mathematics and also in real life have only partial symmetry. So an example is, for example, an equivalence relation. Equivalence relation, you have a pair X and Y, which is in relation, and you can flip them around. And also, if you have X is in relation with Y, and Y is in relation with Z, then you can also concatenate these pairs, and you get that X is in relation with Z. Group bundles, for example, if I have a bundle of circles, then I can multiply the elements which lie in the same fiber of this group bundle, but I cannot multiply, for example, points which lie in this copy of the circle and points which lie in this copy of the circle. So I have only partial symmetry here. And maybe also an example from algebraic topology that's also relatively elementary. You take all the paths in a topological space and you mod out homotopy with fixed ends. Then this object here carries a natural algebraic structure because you can concatenate paths and you can also concatenate homotopy classes of these paths, but you cannot concatenate all the paths because, I mean, the endpoint and the start point of the paths that you want to concatenate, they need to coincide, of course. So you again have some kind of binary operation on the set of homotopy classes of paths. And you also have an inverse because you can just parameterize the path in the other way. And structures like these, all these types of structures here, are special cases of a more general structure, which is called a groupoid. So a groupoid is essentially just like a group, except that the multiplication is defined only on a certain subset. So you are not allowed to concatenate or multiply all elements, as you are not allowed to concatenate all paths, but only on a certain subset it is well defined. This is, of course, not a formal definition of what a groupoid is. There are, I think, two standard approaches to defining what a groupoid is. One is the categorical approach, which is just saying that a groupoid is a small category in which every morphism is an isomorphism. Yeah, it's not the most enlightening definition, and the more verbose definition is would take a long time to completely state. So I will go for the remainder of this talk just with this intuition that you have a group, but only a group of, the intuition that it behaves like a group, but the multiplication is only defined partially. And I will soon get to an example of this. And just to convey to you that this is not a completely absurd thing to do. Groupoids are actually routinely used, for example, in algebraic topology or in non-commutative geometry, and also in the theory of C-star algebras. And actually, they have already also been used by, for example, Mackey in ergodic theory to, quote, bring to light and exploit certain apparently far-reaching analogies between group theory and ergodic theory. So this is by far not the first case that someone tries to use groupoids in dynamical systems or in some other area. Okay, let's get back to our idea. We had this simple case where it was easy to characterize isometric systems in terms of functional analysis using Peter-Weyl compactification. Now, what we can do is to encode both information about K, phi, and also about this extension, is to take this group here, but we slice it into many, many parts. So we take all these powers and we restrict them to all possible fibers. And then we, of course, do not end up with a group anymore, because if I have maps, a map restricted to a fiber, it just maps to another fiber, and maps between different fibers I cannot necessarily always concatenate. But in some cases, if the target fiber, the initial fiber coincide, then I have a reasonable concatenation operation and also an inverse operation. And so one obtains a groupoid here. Now, this groupoid, one can try to compactify it to obtain an enveloping groupoid. And how would one go about this? Well, one has all these maps between different fibers. Now I want to say what it means for maps which map between the fibers to converge to other maps which map between fibers. Yeah, here you need to make a small trick, or at least it's easiest if you make a small trick, and you look at a map which is just defined on some fiber and maps to another fiber as represented by its graph. Because if you represent the function this way, you realize it's just a compact subset in some larger compact space, namely in k times k. And on the closed subsets of a compact space, you have natural topologies, Chaboty-Feld topology, Vietoris topology, whatever. It's all the same in this case. And then with respect to these topologies, you can have a natural notion of convergence, and you can define an enveloping groupoid. And then, once you have done this, and I mean, this takes a lot of work to work out formally. But once you've done this, you can also prove some version of the Peter-Weyl theorem for compact groupoids. And from this, you can then deduce, in fact, this more general characterization of isometric extensions, which in particular gives you back this initial characterization if the extension is trivial, so if L is just a point.
Excuse me, did you say the second step? What are these functions that we see there?
These here?
Yes.
Okay, here is a picture.
Ah, okay.
So we take the powers of phi to the k as above. But now we slice them into little pieces along the fibers, because we can't just take this group here. We somehow need to encode information about the extension also. And this we do by restricting all these functions here to all possible fibers. And then I get functions which map from some fiber KL to some fiber K psi of L. And this is what phi restricted to KL does. And then analogously for higher powers of phi. And then sometimes I can concatenate them. So for example, if I have this map from the fiber L to the fiber psi of L, and then I have another map which goes from psi of L to psi squared of L, then I can concatenate these two in a meaningful way. But for example, if I have a map over here, which is defined on the fiber L prime here, and it goes to psi of L prime, well, I cannot concatenate this guy here with this guy. It's not going to work. So the concatenation or multiplication, there is a canonical one, but it is only partially defined. And I also have a canonical inverse. Okay, has this made the notation clearer?
Yeah, now it's clear. Now the question is only what is the envelope incorporate, but this I don't know if you have a picture.
So actually, this is we wrote a long paper about this, and maybe I can tell you more about this during the discussion. I can show you an example later. Yeah. For now, I will try to move on because I cannot go into the proof here too much because there's a whole theory for itself. For now, we will try to use this here as given this result, and I will state it again here. So our original wish was to have this characterization in terms of finitely generated invariant submodules. Actually, our wish comes true, and it gets even better. So, Knapp needed minimal distal systems. We don't need that. So we can do it without the distality, and actually also without the minimality, which is interesting. So instead of minimality, which is the standard assumption that you will need in books by Bronstein, by Auslander, and often also by Ellis, instead of this, you can get away with something much, much weaker, which is just that you have no non-trivial invariant functions. And this is fulfilled by all transitive systems, is fulfilled by all chain transitive systems, systems with, nice attractors, things like that. So a much, much larger class. And the only price that you pay is that you need that the extension is an open map, but openness is, and also this condition here for the invariant functions, these are both implied by being minimal and distal. So this is really more general. Okay, and the only thing that you need to keep in mind is that if you get rid of the minimality, you pay a small price. Namely, the modules that you need to use get slightly more complicated, and you need to add one adjective, and this is that these modules are projective. And it's not, it's only apparent, it only appears to be more complicated because actually in the setting of Knapp, the modules also turn out to be projective. And here we, because of minimality, and if you don't have minimality, you need to require this. Now, quick recap from like algebraic topology, what these projective modules are. So a module over a ring is called projective if there is a module gamma tilde such that sum is a free module. And somehow the main reason why this projectivity suddenly comes here out of nowhere is the Cs1 theorem. So somehow the Cs1 theorem is hiding under the hood here. And the Cs1 theorem just says that if you have a compact space, then there is an equivalence of categories between locally trivial vector bundles over the space and finitely generated projective C of L modules. So this explains a bit why you get these finitely generated projective modules here. There's a Cs1 type theorem with locally trivial vector bundles hiding. Okay. For us, these projective things are not so important. For now, we will move on and we will try to use this because this is what we set out to find. We tried to find functional analytic characterization of isometric extensions. Because once we have the characterization, our hope was that finding topological models will be super easy, as it was in the very beginning when we tried to find topological models for systems with discrete spectrum. We just wrote down the algebra and then we were done. Okay, so extensions with discrete spectrum. Here's an example. Yeah, maybe it's illuminative to quickly do the example. So what do these modules look like? Well, let's take our favorite extension. So we have the skew rotation as an extension over the usual rotation. And then we consider the following functions. So in the first component, we do nothing. And in the second component, we take these characters. So x, y gets mapped to just y to the k. And then if you plug this into the Koopman operator, I forgot the evaluation here of x, y. Then what you see is that you just get the function you started with multiplied in the module sense with this same character. Okay, but what does this tell us? Well, we know the space of continuous functions is spanned by all the characters. So characters which depend in x and characters in y. And this is certainly the same as if I take all the functions which are just a character in the second component times k, independence of k. And then we take this module operation which comes from the factor. So this allows us then to write here, instead of the 1, an arbitrary function. And then, of course, we get, in particular, all of these functions here, and hence all of the continuous functions on the two-dimensional torus. So what do we have here? These expressions here. These are submodules, because I mean it's just a function multiplied with all possible functions from the factor. So it is by the definition a submodule. And it is finally generated because it is generated by just one element. I just take one function and I multiply it with all continuous functions which come from the factor. And all these finitely generated modules here, submodules, they generate the entire space of continuous functions. And then in principle, one would also have to check like the other axioms that are, or properties that I wrote down, like projective and closed and all of that, but it's not so hard to do this. Okay, now an extension of ergodic measure preserving systems has discrete spectrum if. And there are like a ton of different definitions, and they are essentially all equivalent. And if we now come from this topological approach, then somehow, I mean, the easiest definition to work with would be the following. And it's, I mean, we will not work with this because we will have an equivalent characterization. But let's go through it. So it has discrete spectrum, essentially, if we have many finitely generated projective closed invariant submodules in L infinity of x, and many means they are dense in L2. Okay, you can already imagine that it's not fun checking all these properties here. So we make the following remark. If you have a finitely generated invariant submodule, then it is always contained in a free and hence projective and closed submodule. So the upshot of this is this property here is just equivalent to saying I have many finitely generated invariant submodules. And so the entire property of having the discrete spectrum can also be phrased very, very simply. with like these two properties, finally generated, invariant, and then submodule. But it will be very important for us to have the bridge towards topological dynamics to know that this is equivalent to having these other more complicated properties. Okay. So finally, our goal was to construct topological models for discrete spectrum extensions. And I claim that now we can do it. So step 1, characterize isometric extensions. We have done this. Step 2, find a good subalgebra for a topological model. And this was super easy when we did it earlier, and hopefully it will be the same now. So our goal is to prove the following theorem. Suppose we have an extension with discrete spectrum of ergodic systems. Then we want to show that there's a canonical topological model for this extension, which is isometric or pseudo-isometric. Okay, let's try to prove this. But before I go to the next slide with, somehow I think my presentation disconnected.
Yeah, I cannot see the after step 2, nothing.
Yes, exactly. I noticed. Give me a moment. I will try to reconnect it. That is unfortunate. Yes, let's reconnect. Okay, I'm back here. I am sharing my screen again. Here you go. Share. Then presentation mode. Okay. Okay, here. So here's the theorem, and now you should be able to see it. Okay, so I repeat. We want to show that for a discrete spectrum extension of ergodic systems, there's a canonical topological model that is a pseudo-isometric extension. So just making the step from this discrete spectrum in ergodic theory to isometric extension in topological dynamics, canonically. Okay, and the proof will fit on this one slide. It's just as exactly the same strategy as before. We start with the discrete spectrum extension of ergodic systems. And then we need to find two topological models. We need to find a topological model for y psi, and we need to find a topological model for x phi. Well, if we start with y psi, it's hard to find like a canonical model. What is a canonical subalgebra? We don't really know anything about y. So the easiest subalgebra to take is just L infinity of y. And then you get some topological model, L nu psi for y psi. And here I'm doing like a bit of abuse of notation because I don't want to introduce too many variables. So I don't know the dynamics on the original system and on the topological model again with psi and later also with phi. So now we need to find the subalgebra for A. Here, well, we know what we want at the end. At the end, we want this property with the many finally generated projective closed invariant submodules, which is equivalent to being an isometric extension in topological dynamics. So we just take all of this and we plug it in here. And then we take the closed linear span in L infinity of x. And one can show that this then defines a C-star subalgebra of L infinity of x. And because we assume that the extension has discrete spectrum, this subalgebra is also dense. And as I said, the denseness is important. Okay. And then we obtain a topological model for x phi. And then, yeah, this inclusion from between these subalgebras, because B is contained in A, because L infinity of y is in particular one of these submodules. It occurs as one of these submodules. One one obtains thus a C star embedding between B and A. And on the level of topological models, this yields an embedding between C of L and C of K. And then Gelfand strikes again and tells us this abstract C star embedding is actually given by Koopman operator for some extension Q. And then we are basically done, because then we plug in what we know by construction. A is isomorphic to C of K. And if we use this isomorphism to translate everything, then we see that C of K just fulfills exactly what we need. So there are many finitely generated closed projective invariant C of L submodules, which is a mouthful, but the only thing we need to know is that this is equivalent to being an isometric extension, if the linear closed hull of these is everything. And yeah, we defined A just so that it works. Okay, and then we can conclude that the topological model is an isometric extension. So it's just as easy as in the case that we did before.
But where did you use the groupoid? I mean, I think this one could have guessed without knowing about the groupoid.
The groupoid you need for the characterization theorem. I mean, you need this characterization here.
I see.
Yeah, because otherwise you don't get back, and also it's not so clear. I mean, if you have an isometric extension, that you get all of this here. I mean, it's not exactly obvious, and so this is where this groupoid stuff enters.
Mm-hmm.
Okay. Now let me go back. Okay. So, and now the last step. We now just need to fit everything together and build topological models by going up the tower. So let's go back to our foundational example. We have the skew rotation, and we know, so we regard it as a top measure preserving system. And then we have this factor here with discrete spectrum. And then we can apply the machinery that we saw to construct a topological model for this system, ignoring that it is already a topological system. And then we get back the same system if we apply this topological model procedure. And why did I pick this example, which is a bit silly? Because now something interesting happens. So if we try now to do the next step, then we run into trouble. Because in the end, we want a minimal distal model. The theorem that we just proved tells us if you have an extension with discrete spectrum, then you can find a topological model at the top and a topological model at the bottom, such that you obtain an isometric extension. But that's not good enough, because we want to build a tower. We already have a system at the bottom, and we want that the topological model that we obtain here is an extension of the topological models that we already bring with us from the previous induction. So if we have just a theorem which tells us, okay, you have an extension and you can change the bottom and you can change the top such that you get some nice topological model, then that's not so useful if you want the bottom to be something specific. So actually, the theorem that we proved is not quite good enough. So that's just reiterating what I just said. We need to find topological models for extensions with fixed bases to build towers. And so there is a strengthened theorem, which goes as follows. And with this, we will succeed. So if you have a discrete spectrum extension of ergodic systems, and you already know that the system at the bottom is a topological system with, and the measure has full support, then you can find a canonical topological model, which is, again, isometric. I didn't write this here. Okay. So here it should say it is isometric. Sorry for that. And important, you can use the same base. Okay, if you want to prove this theorem, the proof is essentially the same as the proof that we just saw, where we were allowed to change the base. So what we are going to do is really just the same, just with a few changes highlighted in red. The first change is the base is fixed. So there we have a fixed subalgebra which we need to use, and this is just the subalgebra of continuous functions on L. And then we run into trouble because here this also changes. Here you get a C of L. And why is this bad? This is bad because you know that there are many L infinity of Y submodules in an extension with a discrete spectrum. But you don't know whether there are any C of L submodules, because C of L is much smaller than L infinity of L nu. So, I mean, this entire guy here could just be empty or zero, because you don't know whether there are any Z of L submodules. Whew. And this ties back into the problem that I announced. Is A dense in L2? That's the central problem. And this is far from obvious, but it is true. So here's the problem. We know that there are many invariant L infinity of L nu submodules, but we need invariant C of L submodules with respect to a smaller subalgebra. Okay, and yeah, you can prove a lemma that under the above assumptions, every free finitely generated invariant submodule with respect to L infinity of L, so we have such a submodule gamma, is the closure of C of L submodules it contains, which are finitely generated and free and all of that. And the proof relies on a technical theorem by a guy called Derrien, which maybe I will not go through in detail now since the time is almost up. I will just say that it's a co-cycle approximation theorem which is behind this. So Derrien shows that if you have a measurable co-cycle into unitary matrices, then you can change it on a small subset and obtain a cohomologous continuous co-cycle. And with this perturbation argument, you can then show that you can find continuous submodules. Okay. So yeah, then you can prove this theorem, which I already announced, that this is just the same that we had earlier. If you have a discrete spectrum extension with a fixed base, then you can find a canonical topological model that is an isometric extension, again, with the same fixed base that you had before. And yeah, then you can do this, revisit this example, and you see that it works out because now you can find here a topological model that is an isometric extension of this guy here at the bottom, which we fixed. And with that, we are at the end. So one can then prove that an ergodic distal system has, in fact, a minimal distal model. Lindenstrauss already told us this, but this minimal distal model is actually completely canonical. And as I indicated, it's actually a functor. So you have the category of distal ergodic systems and this category of minimal distal systems endowed with some ergodic measure, and then you have this topological model functor here. And yeah, so there's actually a categorical relationship between these two classes of dynamical systems, which pops out of better understanding isometric extensions and approximation properties of submodules. So whether you can find certain submodules and certain properties. And with that, my time is up. So yeah, thank you for your attention. And if you have any questions, then I would be glad to answer them.
Thank you very much. Let's thank the speaker. I think this was a very interesting talk, and this is very abstract, but you did, in my opinion, a very good job. Are there any questions? If not, I actually have two questions. So
Yes.
The first question is, the paper of Lindenstrauss is, of course, about the impossibility to build in general the uniquely ergodic distal minimal model.
Mm-hmm.
And he gave a sufficient condition, which is that the groups are connected.
Mm-hmm.
In my work with Lian, we gave another condition, which is too complicated to state, but I would like to ask you if this new work sheds light on the question of the if and only if question in the context of the uniquely ergodic distal minimal model. So to find the, the condition that is equivalent.
Yeah, yeah. So Henrik and I, we actually thought about this problem with the unique ergodicity from time to time, but we, as of now, I don't think we have a better understanding of this problem using this approach.
I see. My second question is something you mentioned, and you said you will say it, but as far as I got it, you didn't say it, and you said
yes,
about why it doesn't work for the more general group actions.
This is hidden because at the end I ran out of time. It is hidden in this result of Derrida. It's co-cycle approximation, and it's much harder. If
of course, I should have guessed that. Yes.
So this is the one and only place where the fact that we are using Z actions enters.
Yeah, but it makes sense. I agree with you, of course.
Yeah.
Okay. If there are no other questions, let's thank the speaker again.
Thank you.